Ultraviolet spectroscopy, which is UV spectroscopy, it's a spectroscopy technique that we use in order to determine if our compound is conjugated or not, meaning that it needs to have 3 or more p orbital. Then if this is the case, then your molecule is going to absorb in the wavelength region between 200 and 400 nanometers. This is the UV region. The more conjugated your molecule is, the higher is the wavelength of absorption. So your wavelength of absorption is going to be shifted to a higher wavelength. The absorption of radiation differs from one spectroscopy technique to another. For example, in IR, bonds vibrate. In NMR, proton spins, and in UV, electrons get excited from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Consider alkene. Alkene is not a conjugated system. So if it's not a conjugated system, it's not going to absorb between 200 and 400 nanometers. It's going to absorb before 200 nanometers in there. Alkene has 2 electrons and it has 2 p orbitals. So the number of pi molecular orbitals are going to be 2. Now, since it has 2 pi molecular orbitals, we go ahead and we draw them. We put the number of electrons in one of them, we fill it completely, and that is going to be the highest molecular orbital that is occupied. And then we shine a light on that highest occupied molecular orbital. If the energy of light is equal to the energy between the 2 molecular orbitals, the electron is going to be excited into a higher molecular orbital. That excitation, we call it a transition, and we represent it by the motion of the electron. So here the electron is transitioning from pi to pi star, so we show it from pi to pi star in there, indicating that the electron is going from a lower molecular orbital level to a higher molecular orbital level in there. So now after the excitation, your highest molecular orbital is going to be the pi star, because this is going to be the highest molecular orbital that is filled. And it's going to have an unpaired electron in it. Let's consider the 1,3 diene. The 1,3 diene has 4 p atomic orbitals. The number of atomic orbitals should be the same as the number of pi molecular orbitals in there. And you already know the number of electrons because every p atomic orbital has 1 electron, so that is a total of 4 electrons in there. You draw your molecular orbitals, you have 2 bonding and 2 anti-bonding. For every bonding molecular orbital, there is an anti-bonding one. So after this, you go ahead and you fill your electrons in there. Make sure that every molecular orbital has a capacity of 2 electrons. So now your highest occupied molecular orbital is pi2. After you do this, we're going to check the UV absorption. So you shine a UV light on the highest occupied molecular orbital. So this is going to be the highest occupied molecular orbital in there. So the electron now from the highest occupied molecular orbital is going to get excited, meaning that it's going to transition from pi2 to pi3 star. And this is going to be the motion of the electron after it gets excited in there. So you would see a signal because your system is conjugated. You would see a signal around 220 nanometers. And that is going to be your maximum peak. The UV spectrum is a plot of absorbance versus the wavelength. And if you extrapolate the maximum peak to the x-axis, then you get the wavelength of excitation. You always need to determine the transition state. And to determine the transition state, you have to draw your molecular orbitals. You start by figuring out how many p atomic orbitals you have. This is equivalent to the number of pi molecular orbitals, and then you count your electrons. Every double bond is a 2 electron. So here you have 6 electrons. You have 6 p atomic orbitals, and there divide them in half. So 3 are going to be bonding, 3 are going to be anti-bonding, and then go ahead and fill your molecular orbitals. The highest occupied molecular orbital will be pi 3. So when you shine a UV light, that is going to be on the highest occupied molecular orbital. So your transition now is going to be from pi 3 to pi 4 star. Since your transition now is a higher molecular orbital, your wavelength of excitation is going to be higher. So let's have an example over here. You don't have to draw the molecular orbitals to determine the excitation. So go ahead and count your number of double bonds here. So the number of double bonds is equal to 6. This means that I do have, because I know every double bond is a 2p orbital. So I have here 12p orbitals in there. This means that I'm going to end up having 6 bonding and 6 anti-bonding with the 12 electrons. So now my transition is going to be from pi 6 to pi 7 star. And as you can see over here, the more double bonds, the higher is the wavelength of excitation in there. And as the wavelength of excitation approaches the visible region, then you're just going to go ahead and show color. In this case, this is more than 400 nanometers. It's 550, 550. This is the red region. For systems that are conjugated and have a heteroatom with lone pairs, these lone pairs, they also undergo excitation whenever they are hit by UV radiation. You just want to know where these lone pairs belong, because they don't belong to the pi molecular orbital. They don't belong to the p orbital. The p orbital of the oxygen, because oxygen here has a p orbital that has 1 electron that overlaps with the p orbital of this carbon. So this is going to push those lone pairs outside the p orbital in there. So these lone pairs, normally they belong to a non-bonding state. We call it an end state. And that state is between the bonding and the anti-bonding. So you have here bonding and you have an anti-bonding in there. So you do have a system of 2 double bonds. So this is going to be 1, 2, 3, 4 p orbitals. This is going to be 4 pi molecular orbitals. You draw your 4 pi molecular orbitals, divide them in half. Now between the 4 pi molecular orbitals, you have a non-bonding state. In this non-bonding state lies the lone pair. This is why we call it a non-bonding state. So this is how we put the electrons of the lone pair. The electrons of the lone pair has nothing to do with the electrons of the double bond. In the double bond here, I have 1, 2, 3, 4. I have 4 electrons. And then I have another 4 electrons in the non-bonding state, which is the lone pair. So you go ahead and you fill your electrons. Now, the non-bonding state has 2 levels of the same energy. So when you want to fill those levels with electrons, you would need to start filling 1 electron at a time. You cannot fill each level to its maximum capacity and then go on to the next one. So you fill 1 electron in 1 bonding state, and then you go to the other bonding state and you fill an electron. Then you go to the other one and you fill it to the max. And then if you have any left over, here we go ahead and fill the other non-bonding state to the max. And this is how you fill states that have the same energy. So now the highest occupied molecular orbital is the N. So if you do a UV excitation, then your excitation is going to go from the N, or transition is going to go from the N to the pi 3 star. And now your pi 3 star is going to be the highest occupied molecular orbital in there. Since N is a higher energy state than pi 2, then we are expecting the transition from N to pi 3 star to be at a higher wavelength than the transition from pi 2 to pi 3 star.